Okay, so here we go.
Right.
Okay, can you see?
Yeah.
Can you see this, Bruce? Okay, so here we go. We're going to go at the other extreme. We're going to look at cosmology, or the macrocosm, and we'll break it down into two sections. So we've got some pictures here. Uh, this is Edwin Hubble, and there's another guy here you've probably not heard of, Vesto Slipher, who did the original observations with optical telescopes, and Hubble did a lot more that showed that the universe was expanding, that all the galaxies were running away from one another. This other guy over here, Fritz Zwicky, worked with Hubble, and he looked at this one spiral galaxy and wanted to know, was it stable if it was spinning? And he was able to show that it wasn't stable, with gravitation being the only force, unless there was a lot more gravity due to matter that he couldn't see. So he was German. He called it dunkle matter, which is dark matter. And there's 4 times as much dark matter as there is matter in our universe. And this woman here, Vera Rubin, followed up in the 60s and early 70s, did all these incredible observations that confirmed what this guy here, Fritz Zwicky, had done, that that showed that a lot of the universe is made up of dark matter. And that's what it's been for 50 years now. Is the physicists don't even talk about it. They all they say is, well, 5% is matter and 95% is dark. And they're all racking their brains. What in the world could be the dark matter? What could be the dark energy? What's going on here? But 50 years in, I don't have anything to show for it. This guy up here is Alan Guth. He's a classmate of mine, and he came up with this idea about how when you look at the stars at night, they appear to be uniform all over. And so he came up with the idea of a phase transition, like when water that's liquid turns into steam. You end up with a phase transition there from liquid to gas. And so he postulated that at the start of our universe that there was a huge inflation that took place, and that appears to be what Ron Cowan observed, confirming this theoretical idea. And then up here, we got Isaac Asimov, who wrote this great short story called The Last Question, which deals with all this stuff. So, and Asimov was anticipating what the Hindus said, that there's cycles in the universe, and they bounce, and they expand, and then they collapse, and then they bounce back again. So universe is created again and again and again.
Who's that guy on the upper left?
This guy is Alan Guth.
You didn't talk about him.
Yes, I did. I said he covered inflation.
Concepts found in various cosmologies, most notably the Big Bounce theory,
So,
which suggests the universe undergoes an infinite series of
okay.
expansions and contractions.
So here's a little timeline.
Why your phone is doing it.
It's your phone.
This is not my phone. But
Yeah.
you're right.
So the thing here, this is really a modern thing, cosmology. It really started in the 1900s, just before that, when optical telescopes got to be good enough so that you could start to really see the stars out there in greater detail. You had to gather more and more light to see this. So really, it's been really 100 years of this that has led to what we call cosmology today, and huge amount of activity over this period of time. Initially, there's optical telescopes, as we said here, and they were used down here by this guy Vesto Slipher to discover that the galaxies are all moving away from one another. Up here was this guy, Edwin Hubble, who actually didn't just do it qualitatively, he measured quantitatively how fast things are expanding. That was in 29. And then if everything's going away, everything started from a common point. So in 1927, there was a priest, no less, Georges Lemaitre, who said, oh, there was a big bang, just like when you read Genesis in the Bible, it said, let there be light, and there was light. So see, so the church is getting in on this. Then we talked about this guy, Fritz Zwicky, who was looking at the galaxy spinning and that they wouldn't stay together unless there was extra matter, which he called dark matter. And then we skip over all of World War II is in here, where there was a huge amount of advances in microwave technology, and that led to radio astronomy and microwave radio astronomy in particular. So these two guys, Arnold Penzias and Robert Wilson, took one of these microwave transmitter receivers that AT&T had built. They put a communications satellite into orbit called Telstar, and that was in like 62. And they used it for a while. And it became clear that really what you wanted were either lots of very low Earth orbit satellites or satellites that orbited the Earth once a day, which are called synchronous orbit satellites. And what AT&T had built wasn't going to do the job. So they had this telescope there, and they were cranking it up, and they had this background noise they couldn't get rid of. And they went over to Princeton and talked to some of the faculty there at Princeton, and these guys published a paper on their background noise there that was in their radio telescope, and the Princeton guys published their paper right behind it, saying, here's a theory that explains what they observed, which was the Big Bang. And if you read the paper, they didn't really say anything. They just said, we've got this noise here, and there's this other paper right behind us that's going to give you an explanation for it. So that shows you what happens. They ended up getting a Nobel Prize for this in 1977, I think. Then something that's near and dear to me, in 1968, Arthur Clarke collaborated with Stanley Kubrick to produce a really great science fiction film, A Space Odyssey, which is clearly part of this cosmology activity. In 1970, Vera Rubin had kind of completed a huge number of observations all through the 60s, showing that there really was dark matter everywhere. Here's Alan Guth out here in 1979. And then there's this huge gap here, and except today when we have this thing called 3I Atlas that entered the solar system. This appears to be, it's the third one that's been observed. The first one was called 1I and was observed by somebody, so they gave it a name. Oh, Umura. Here they gave it a Hawaiian name. I don't know why. That was like 2015, 2016. Then 2017, there was another one, which was 2I. So that was the second one. I for inner space, whatever. And then that was called after the guy who discovered it. And this is 3I Atlas. And Atlas is an acronym for a network of telescopes that are looking around for these objects that NASA and other countries have funded. So Atlas it's an acronym. It doesn't have nothing to do with Atlas, the Greek god. So this thing is running around our solar system right now. And there you have it. There's really, this is what makes up what we would call cosmology today. A lot of observations. The thing that's hidden in here, remember the first Russian space satellite was Sputnik in 1957. And when we go up to today, every single planet in our solar system has had at least one space probe go near it. Typically, things like Mars have had many, and we actually know a lot more about our solar system now than we knew back in the early 1900s. But in the cosmology side, we were at square zero. And here we've had all kinds of work done with all kinds of telescopes. So initially optical telescopes, radio telescopes, and then going into today we have X-ray astronomy and gravitational astronomy. We can detect gravity waves. So technology's improved through the whole time. The theory hasn't kept up with it. So here we go. Here's what we saw before 1900s. We had eyeball observations, and people could pick up wandering stars, as they call planets. There were comets, there were stars in the sky, and they picked up on there being the pole of the Earth precessing in a 26,000 year cycle. It would move through every 2,100 years, it would go through another house. And there are 12 houses that we know from astrology. So that's what we started with, just eyeballs. Then we end up with Galileo. He had a telescope in 1610. He started to look at it. He found there were craters on the moon, and he saw moons running around Jupiter. And that suggested to him that the Earth wasn't the center of everything. Probably the sun was. But he had to be quiet about that because the church was going to burn him at the stake. Then we had more telescopes advance beyond Galileo, and Halley discovered this comet in 1685, which comes every 86 years. And when did it come through? It came through, I'd have to go look. Came through in the 1990s, 1980s, something like that. It was kind of a bust. It was early in the 1900s, like 1910. It was spectacular across the sky, and everybody went ooh ooh. But it was 1910, and 86 years would have been 1996, and it was really a bust. It wasn't at all spectacular like what had happened in 1910. Then we had it wasn't Halley, it was somebody else who discovered Uranus. So this is the first planet that was discovered using telescopes. And then there was a whole bunch of discoveries here dealing with the asteroid belt. Ceres, Pallas, and Vesta are all large asteroids. And what happened in the 1960s was a guy in Bethesda, Maryland, at the U.S. Naval Observatory took plots of all kinds of asteroids and comets, and he put it onto a computer and ran it backwards in time. And he saw that they seemed to all come out of what would have been a planet 3 million years ago that blew up and created all these things. And his reward for doing that was they immediately censored him, and the book was like impossible to get until recently. But most people believe that's what happened. Neptune was discovered because the orbit of Uranus had little wobbles to it, and it was determined that was probably due to another planet. That planet was Neptune. There's another asteroid here in 1849. And then 1894, Percival Lowell at Flagstaff, Arizona, just outside the Grand Canyon, was looking at Mars, and he discovered channels, or what he called canali in Italian. And of course, got misinterpreted to be canals. There's clearly been water and oceans on Mars, and Mars apparently appears to have been creamed by something massive, a gigantic asteroid or something. And from the space probes that are in the orbit around Mars, there's enough evidence now for isotopes of different sorts that it appears there was a nuclear war on Mars, which didn't do them any good. So there you have it. That's what we started from going into the 1900s. And so now let's look ahead. And we're going to go through them one at a time. Here's this guy, Vesto Slifer. He should get an award for this name. I can't imagine what his parents are thinking when they named him this. But he succeeded Lowell at his observatory, and he did all these measurements going right into World War I of the little blotches of stars that turned out to be galaxies. They were literally like white smudges. It was very hard to figure out anything with the telescope that he had, but he did the best he could. And that got a lot of people interested in this. So the majority of these galaxies that he observed were moving away at high velocities. He just flagged that. He published his observations. People heard about it, and this leads to what's called the so-called redshift. This is where if things go away from you, the wavelengths get dragged out. They get longer, and longer wavelengths mean you're moving toward the red side of the spectrum. And it was done at very high speeds, is what's going on here with these things. A good fraction of the speed of light for some of these things. But he didn't have any way to measure how far away these things were. He could see by the shift in the spectrum that this is an indication of high velocity, but that didn't say anything about how far away they were. But he did a great job. And that takes us over to Einstein, who worked up a new theory of gravity in 1916 called general relativity. So here, what we did, here we see a mass, which we show as the Earth, and we see space itself being curved by the mass of the Earth, so that things get attracted to the Earth as they get closer, they fall down into this gravitational well that the Earth forms by deforming space. And that's what Einstein felt was what was going on. So the gravity is not really a force as we know it, but it's a curvature of space and time that's caused by this mass and the energy associated with it. So general relativity can explain these really massive objects like stars and planets and how they distort things with this force of gravity. And it was a generalization of what Newton had observed back in the 1680s when he published his book on Principia on all of what he saw with all kinds of observations that he fit to his theory of gravity. And this led to the notion of what's called gravitational lensing, where if you have light and it comes by a star, and the star is so massive, it'll bend the light, and bending light is the same as making the light go through a lens. So this is what Einstein believed. That's great. The only problem with this is that Nikola Tesla was around at the same time, and Tesla said, no, this is not right. He says space doesn't curve. Space is just space, but it's filled with an ether. And the ether is what causes gravity. So if we have different densities of ether, if ether is more dense, say where the Earth is, then we have more gravity here. And if we go out away from the Earth, out into space, then there's less ether. And so there's less curving here, like we see, and gravity drops off. I'll argue that Tesla was right and Einstein was wrong. We'll see. Now, this stimulated, because of this work by Einstein, a lot of people to look at this. And there was a Catholic priest, George Lemaitre, who said, I see what's going on. If everything's moving away from everything else, then it all started off in some common place. And that is what led to what's called the Big Bang, which is the start of our universe. And that came about. The term was really, it took a couple decades for people to like it. And they, in the late 1940s, it finally caught on. But he ended up being attacked for this. But the problem was when Hubble finally came out with his observations of what was going on, people had to start taking him seriously. That there really was some sort of event that led to the start of our universe. So, having said that, he's a theoretician. He's not an experimentalist. We go to Hubble, and Hubble had this telescope at Mount Palomar, just outside of Los Angeles. And what did Hubble do? Well, he knew what Slipher had done, so he took this velocity data that Slipher had gotten by looking at the shifts in the spectrum of light of these different galaxies, and he had his own ideas on how to measure distances. And this gave him something that there was a direct relationship between a galaxy's distance and its velocity. And if you believe in this, if the farther away you are, the faster you're going, if you believe that, then this suggests that space itself is expanding. And that was the key thing. This is the thing that makes space expand is going to be called dark energy. Now, here's a colleague of Hubble who in 1933 did this analysis, and he looked at this one coma cluster of galaxies. Here it is here. And they were moving, spiraling around, as you can see. But if they're the rates at which they're spiraling, are again tens of thousands of years, hundreds of thousands of years to do a spiral. Okay, so he went ahead and he assumed something about the mass of each star in this galaxy is roughly the same mass as our sun, and there's maybe 100 million of them there. And if you believe that, then if they're all attracting one another by gravitation, this thing is going to fly apart. It's going to go every which way and it's going to disappear. But we can see it. It hasn't blown apart. So what he came up with was there had to be extra matter there, which he simply called dark matter because he couldn't see it. And this got people interested in this. But what people didn't like was there's over 5 times as much dark matter as matter, which makes you wonder what we're studying. Then we come over here to these two guys, Arno Penzias and Robert Wilson. Penzias just passed on. Wilson is still with us. And they had this radio telescope, and they were measuring, using it to do astronomy, radio astronomy, but they had this noise in it, which they call cosmic microwave background energy, all in the microwave frequencies, and they couldn't get rid of it. They did everything in sight. They had, here you can see a picture of this horn there, and of course pigeons go in there and do their thing, so they cleaned out all the pigeon poop. That didn't do it. The noise was still there. And then they went over to Princeton and talked to this physicist Robert Dicke and his students, and Dicke said, oh, this is a remnant, it's the remnant sound of when there was a bang that started off our universe. And so they got the Nobel Prize for this, like I said, in the 70s. And there's been many, many, many experiments since then to justify this. A lot of them, they go into space. So this is a picture taken by one of these space probes that shows the cosmic microwave energy. So the thing you're missing here is it's showing the noise level, and it looks like there's some real variations, that the red is higher than the blue, and it's scattered all over the place. In fact, it's like if you looked at this head on, it's actually they magnified this differences to make it easy for you to see these things. But as far as you're concerned, it would look perfectly uniform. Uh, but they magnified the differences to make it stand out, and so forth. So a lot of people believe, yeah, there really was some sort of bang that took place. A lot of evidence supports it, and so it goes. So there were other theories. For example, there was a Brit, Fred Hoyle, who argued that really matter is just created continuously out in space, and but when he saw this evidence, he had to back off because he couldn't figure out how to explain this background radiation. So the universe initially was at a state of very high density and temperature, is what they're assumed, and then it decayed. So this is time running this way, going from this end here all the way out to the present. And you see here's the very start of things. And this period of inflation that is magnified here actually takes place over 10 to the minus 32nd, 10 to the minus 30th power in terms of seconds. So the universe expanded here by 30 orders of magnitude in under 10 to the minus 30th seconds, an incredible big phase change from being all together to expanding. And then now that it expanded, everything is smeared out uniformly. You can see this picture here of the colors here, and then all the stars start to get created out here 400 million years later, and here we are today. Now, the only problem with this picture is it's wrong. It's a nice picture, but it doesn't match what happens. Ron Cowan looked at the start here, and there was a start to the universe. He witnessed it, but the problem was there was no bang. But there was inflation. Space itself expanded like crazy. That much was there. And then after some period of time was this bang that occurred. All that is true. The other thing is we now have this new telescope that's orbiting on the backside of the moon called the James Webb Telescope, and it's showing that the stars that initially wouldn't form till 400 million years, is showing that those stars form much, much earlier. In fact, going right up to this time of inflation here that occurred. And if that's the case, something is really wrong with this theory. And the thing that Ron observed was there was no fireball, there was no bang, there was no there was this inflation that occurred, but that might have occurred trillions of years earlier than what we're talking about now. And only recently meaning 13 billion years ago, did this bang occur that created this background radiation that was measured. People stand by this. It's amazing that we started the 20th century and didn't have a clue as to what this thing is. And here we are dealing with 13,787,000,000 plus or minus 0.02 billion years ago. Okay, so we know a lot more about when this bang occurred than we did when we initially started. But it's the interpretation of the bang. Where did the bang come from that we're going to deal with? And then we have this other thing here that Ron observed at the start of the universe, called this Higgs boson. Now, there are two types of Higgs boson, one for matter and one for dark matter. So it turns out when you actually look at particle physics and the theories there, you have fundamental particles like electrons and quarks and neutrinos and so forth. And each of these particles has a mass that we physicists have measured, okay? But it turns out the mass for all of these things it consists of a number multiplied by it's a scalar number called the Higgs number, the Higgs field, the Higgs boson. So initially, at the start of the universe, this Higgs boson was zero. It didn't have any mass, and so the particles didn't have any mass. But just after everything bounced and the universe started to get created, what Ron saw was there was a dark matter Higgs boson and a matter Higgs boson that came into effect. And all of a sudden, all of the things for matter and dark matter took on mass. They expanded in mass, which is what we have today. Now, we're going to come back to this. It's interesting because if the Higgs boson went from zero to something, then what happens when the Higgs boson goes back to zero? So keep that in mind. The thing that was done as a theory here, this Higgs boson wasn't discovered experimentally until 2012, and it's been replicated. Now, Ron Cowan saw it under deep meditation, but he saw also the dark matter Higgs boson as well as the matter Higgs boson that was experimentally measured. So we come to a different chap, Phil Anderson. Phil Anderson was a theoretical physicist at Bell Laboratories from the early 60s till 1984, when Bell Labs got changed in the breakup of AT&T, and he left Bell Labs and he went to Princeton, which is where he was when he passed on. And Anderson was one of these people that is off the charts, that you run into him once in a generation. I would go over and have lunch regularly with these physicists that were there at Bell Labs, and Anderson was there one time, and he was going through this whole area of solid state physics, and he was asking these questions, and I said, geez, all of these guys knew who Anderson was. They knew he was very bright, but I was starting to wonder, did Anderson know anything? Okay. Well, then, like 2 years later, I find out that Anderson received some award because he wrote this paper explaining how all this physical phenomenon that he was talking about at lunch, how it really worked, that everyone else had it wrong, and he was just picking it apart. That was how he worked. And he came up with a very enlightening approach to how all these things happen. Well, he did this repeatedly throughout his career. So one of the things that he focused on was the parallels between particle physics and solid state physics. And he came up with an idea that a small change in initial conditions could lead to a very dramatically different final state. So, for example, a material could change a little bit, and instead of it becoming a magnet, it could become a superconductor with no resistance, or vice versa. It could be a superconductor and turn into a magnet. And he walked through these ideas in 1962 about how these bosons could acquire mass through a mechanism that he came up with. And Higgs simply picked up on what Anderson was talking about and ran with it and wrote a bunch of papers on it. But it still took till 2012 for them to actually find this Higgs boson. But the idea came from Phil Anderson here. And he realized that you could have a scalar quantity, something that would go from zero to something that was not zero, and that would give you everything that you needed in your theory, whether it was particle physics or solid state physics. He spent a lot of time on superconductivity and felt that that was a key part to it. He also had the notion that that a lot of the phenomena would emerge, that they had these very complicated systems, all kinds of particles flying all over the place. Very difficult to do a bottom-up prediction by tracking these things. But he in 1972, he wrote a paper called More is Different, where he argued that having more fundamental particles was really not as useful as looking at the phenomena that you'd come up with out of all this. And he showed examples of this in solid state physics, condensed matter physics. So each level of complexity in nature, he felt, required its own set of concepts and laws. And there was a lot of parallels between solid state physics and particle physics and these new phenomena that would emerge out of all this. And he gave lots of examples of these things and so forth in doing this. And so he argued that particle physicists really owed a lot more to condensed matter research than they ever acknowledged. And that's because the particle physicists think they're God. They think they know everything and everyone else is a peon, and they're dealing with the most fundamental stuff. And Anderson never felt that at all. So he developed this shared conceptual framework, and there were analogies between particle physics and solid state physics, and both of them benefited by looking at what was going on in these things. For example, in particle physics, you have the notion that opposite charges, positives and negatives, attract one another, except in the very, very short distances in the nucleus of the atom, when things like protons that are always positively charged attract one another. The positives, the likes attract one another. Well, the same thing happens in superconductivity. In superconductivity, you have electrons zipping along. And one of the things that came out of this was the electrons would attract one another, but the electrons are both negative. They're all negative. So they should repel one another. But in superconductors, the electrons attract one another and they form these pairs of electrons. And that allows them to go through whatever the material is with hardly any resistance. So just example upon example of how theoretical physics dealt with these things. And of course, Anderson got the Nobel Prize for Physics before the rest of these guys at Bell Labs did. And you don't get a Nobel Prize in theoretical physics unless you're really doing off-the-chart work. If you do something experimental, you'll get a Nobel Prize in physics the next year. But theory is theory. So here we have Peter Higgs with his boson, and Peter Higgs ran with this, and he wrote a couple of papers on this, where this scalar quantity called the field or a boson or whatever you want to call it gives mass to all the other particles. He wrote two papers on this in 1964, and he made a prediction about this particle. And then it only took from 1964 to 2012, which is what, 48 years to be able to, and then once they confirmed it in 2012, in 2013, he got the Nobel Prize. Now, here's something else that's interesting to me. In 1968, we had this incredible individual, Stanley Kubrick, decide, I'm going to do the science fiction movie to end all science fiction movies. He called it 2001: A Space Odyssey. So what he did was he spent time with Arthur Clarke, he worked with Arthur Clarke, took a couple of short stories that Arthur Clarke had come up with and put together a script for a movie, which involves these, this is the dawn of time, this is like 1 million BC or whatever, and you see these hominids here that are running around. And all of a sudden, they notice this black monolith sitting here. And the black monolith is doing something, and it appears to be raising the intelligence of these ape-like creatures, and they turn into humans. And we fast forward in the movie from this scene to where they discover one of these monoliths on the moon. It has a very unique electromagnetic field. So they dig it out and they're looking at it. And as the sun comes up over the horizon on the moon and strikes this thing for the first time in, literally millions of years, all of a sudden this thing broadcasts a very strong signal out into the universe. And so this led to them building a spaceship, and they went out to Jupiter and they discovered another one of these things floating around in Jupiter, and that led to the movie. And along the way, there was this supercomputer called HAL 9000 that basically went crazy in trying to run the ship that took them out there to Jupiter. So the special effects in this are equal to anything that we have today. They're absolutely incredible. But what people didn't like about it was the ending of the movie. It seemed to be ambiguous. But what Kubrick said was less is more, that you shouldn't spell out everything. You should leave it up to people to interpret. So he left it that the astronauts that went out to Jupiter returned to Earth, and they're floating around in Earth orbit, but they look like babies. But they're enclosed in some sort of translucent spacesuit, and you make out of that whatever you wanted. Another thing that Kubrick did in this was the movie is incredibly long. It's 2 hours and 40 minutes, but it only has 40 minutes of dialogue to it. So the movie is mostly these incredible pictures that he shot of spaceships and running around through space and on and on. And the dialogue is at a minimum. And so every day when they were shooting, they did all this in London because the Brits gave them a whole pile of money to do the movie. And when they're doing this in London, they would watch the whatever they'd filmed that day, and they just played background music. So we ended up with them. They actually wrote commissioned a score, a musical score for the movie, and Kubrick said, "Let's just throw it away. I like having, the spaceships move through space with the Blue Danube waltz, and I like seeing this monolith here with the music from Richard Strauss, Also sprach Zarathustra." That was who Kubrick was. And so it's the music, the pictures that really make the movie. It stands as one of the top 10 movies of all times. And it deals with the start of the universe. Where did this come from? Now we go to 1970. Here's Vera Rubin, who did these very detailed measurements on dark matter on many, many galaxies that are rotating. And she discovered all of this work, got published and culminated in 1970. And just recently, there's a new telescope that's been commissioned. I believe it's in Chile, named after her because she was a great experimentalist in terms of observing what happened. But what she came up with at the end of the day was 5% of the universe is matter, 27% is dark matter, and 68% is dark energy. We only have been studying the 5% for hundreds of years. The other 95% is just dark. We don't really know anything about it. And so where in the world is it? Well, one way to think about this is if 5% is in 3 dimensions, then 100% is in 60 dimensions. And it turns out, according to Ron Cowan, the right answer is 24 dimensions. So there you go. Extra dimensions hold it, but we don't have any instruments that can measure in the extra dimensions. When Einstein was doing his theory of general relativity, he came up with anomalies that were called today black holes. So these are things that were so dark that light itself could not escape from them. They were perfectly black. And in 1974, Stephen Hawking, who's shown here, wrote a paper on this and showed that they actually do radiate, but they radiate in a funny way that causes these black holes to lose mass and eventually evaporate. But it'll take a long, long time, billions of years. Okay, so even these things, these black holes, are vulnerable to what happens. Now, it turns out in the early 1960s, there was indications that every galaxy, including our own, has a big cluster of black holes in the center of it. So our galaxy has a cluster of something like 4 billion sun masses, which is a lot, but it doesn't take up a lot of space in the universe. And there's other galaxies that have like 100, 200, 300 billion masses of our suns, just incredible numbers in the center of their galaxies. So this all came out of this work on cosmology, and these have now been observed, as I said, in the center of the galaxies everywhere, but yet they're evaporating slowly. This led to a Nobel laureate, Steve Weinberg, who wrote a book called The First 3 Minutes of the Universe in 1977. And he did this to try and intrigue people to go look at this and study this. He went through the creation myth that people have fallen upon, and then went through all of the work of Hubble, the redshifting of the galaxies that actually was proportional to their distance, and then the basic thing today is the universe is isotropic and homogeneous. Even though we have these galaxies that are clearly clumped together, if you step far enough away, it looks like the whole universe is homogeneous and isotropic, and so forth. So this was a very popular book, and there's a lot of other people writing these books. We had Alan Guth a little later dealing with this notion of inflation. Then cosmic inflation was actually a very rapid expansion that occurred just a fraction of a second after the Big Bang, something like 10 to the minus 35th to 10 to the minus 33 seconds after the Big Bang, and the universe grew by at least 26 orders of magnitude in a fraction of a second. And so everything was stretched out. The only problem with this was he didn't have any way in his theory to explain why it stopped. Okay, it does stop. It's been observed. So what's going on here? Then we go to the Hubble telescope that was put in space in 1990, and this led to a whole bunch of new observations here and with not having the atmosphere of the Earth in the way, all kinds of discoveries about dark energy, how old the universe is, and what are called exoplanets. There are now over 5,000 planets that have been recognized around stars around us in our neighborhood. And so this thing has been upgraded again and again, but is an incredible tool. A different sort of orbiting telescope is the Cosmic Background Explorer. This ended up producing this picture we saw before. Was put into orbit, and it mapped out the variations that occurred right after this Big Bang. So it's not quite uniform, not quite isotropic or homogeneous, but it's very close to it. And for all this work, he ended up getting a Nobel Prize. There was X-ray astronomy that started. You can't see X-rays because they can't make it through the Earth's atmosphere. So things are put into orbit, telescopes that could look at things in the X-ray bands, and this led to all kinds of new observations, simply because no one had ever done this before. Also on the top of at the big island of Hawaii on Mauna Kea, there's an X-ray, there's an optical telescope there, and they also have some X-ray work. And this space probe, Chandra, which is an X-ray telescope, has been able to capture things with X-rays 100 times fainter than anything, because again, the atmosphere is in the way, and it's been an incredibly useful tool. And then finally, we went off to gravity waves. In 2015, the first evidence occurred for gravity waves with a couple of collisions that were incredible of stars that generated so much gravity disturbances that they were picked up by this entity here. And what it does, just like this Michelson-Morley interferometer, is it sends a laser down. Here's a laser path, and there's a beam splitter. So some of it will go through the beam, and some of it will bounce this way and that way at a 45-degree angle. So it goes down here, bounces here, comes back, and gets detected here. Similarly, goes down here, bounces, and comes out here. And if these things jiggle enough, you can see a change here. Well, the problem is, what you can't see here is that there's a few wavelengths here of a few thousand kilometers. Okay, so the distances here are gigantic, thousands of kilometers, but the people made it work, and they actually in 2023 started to see all kinds of evidence for these gravity waves. And the final one that I touched on is on the backside of the moon in orbit, this James Webb telescope. It's really keyed on infrared. And so you can see here's what we would see, and here's what the James Webb telescope sees, because the infrared can go through the cosmic dust. There's dust in the way when we're looking at this thing, but the infrared isn't bothered by the dust. And so it goes. So there's all kinds of observations coming out of this thing. So this is the rah-rah story of modern cosmology in the 20th century going up to today. And it continues. There's a lot of money for this, okay? But we're now going to end here, and we're going to just say, look, this is what the 20th century created, was this whole science of cosmology. And now we're going to take a different look at it, about roads not taken and what was really going on here. So just bear with me as we go into part 2. So hold on a second. I'm going to turn off the recording.